One definition of atomic volume is given by the formula. Atomic volume is equal to atomic mass gram per mole divided by density gram per centimeter cube. The table gives atomic volumes of first 19 elements in the form in which they occurs at STP, standard temperature and pressure. A. Outline why many elements have atomic volumes greater than 10,000 centimeter cube per mole. 1 mark question. So let's look all those who have greater than 10,000 centimeter cube per mole atomic volume in the table. So we can see first element, which is hydrogen. Then we have helium, which has greater than 10,000. Then we have nitrogen. Then we have oxygen. Then we have fluorine. We have neon. We have argon. We have chlorine. So that suggests all of them, they are gases. Hence, they have atomic volumes greater than 10,000 centimeter cube because they have less density. So we can write down they are gases. That will give us 1 mark. B. Outline why some of those with the larger atomic volumes have a value almost 11,000 centimeter cube per mole and others almost 22,000 centimeter cube per mole. So let's go back and have a look in the table one more time. As we can see, group 18 noble gases, they have greater than or almost 20,000 centimeter cube per mole, while the other gases, they have around 11,000 centimeter cube per mole. So what's the reason? So we know nitrogen exists as a diatomic, oxygen exists as a diatomic, fluorine exists as a diatomic, and chlorine exists as a diatomic. So diatomic, they will have about 11,000 centimeter cube per mole, and group 18 noble gases, they exist as a monoatomic. So monoatomic. So let's go back and write. So smaller values are diatomic, while larger are monatomic. C. Suggest why some elements such as carbon and oxygen have more than one value for their atomic volume. We know carbon has allotropic form like diamond, graphite, graphene, and similarly oxygen has allotropic form such as ozone. So they have different allotropes. So they exist as allotropes. Hence, there are more than one value for them. D. Explain why atomic volumes of element 11, 12, and 13 shows a steady decrease. So let's go back and have a look. 11 is sodium, 12 is magnesium, and 13 is aluminum. So all three of them, they are metals. So sodium, magnesium, aluminum, all three, they are metals. Sodium, magnesium, and aluminum. All of them, they are metals. Hence, they will have metallic bonds. But metallic bonds will be stronger in aluminum as compared to magnesium and sodium. Because in sodium, there's one delocalized electron. In magnesium, there are two delocalized electrons. And in aluminum, there are three delocalized electrons. Hence, the electrostatic force of attraction between the delocalized electrons and the positive ions will be the greatest in aluminum, then magnesium, then sodium. So we can write down the stronger metallic bonds is the reason. So easy. So stronger metallic bonds. So sodium has the weakest metallic bond, then magnesium stronger, and aluminium the strongest. So stronger metallic bonds, and the reason why is stronger electrostatic force of attraction between delocalized electrons and positive ions. Also, you can write the nuclear charge increases. So nuclear charge increases across a period. So we're moving across a period. So 2 mark questions. So one will be writing nuclear charge increases. The second mark we can say the stronger metallic bonds or stronger electrostatic force of attraction between delocalized electrons and the positive ions. E. Estimate the atomic volume in centimeter cube per mole for element 20. So let's go back and have a look. So from 4 to 12, the difference is 9, 10, and 13 to, so 23, I will write 23. 23. So any value between 20 to 40 centimeter cube per mole will be accepted answer. F. Suggest one reason whether you could ever know the actual volume of a single atom. What range of answers are possible for this question? So we can say no. If we say no, so then we can say probability of finding the electron is low. Probability of finding an electron is low. Some people they can say yes, and bond length can be measured by microwave, and so range of answers, yeah. So simple, no probability of finding the electron is low. 2. A student investigated the effect of storage time on iron 2 content of raw spinach using a titration with 0.01 mole per dm cube KMnO4 in acetic medium. The equation is given. The student acquired the spinach and stored it in the dark in a sealed bag at room temperature. She tested the initial iron 2 content day 1 on 3 samples of 2.0 gram each, and then each day until day 5. The spinach leaves were roughly drawn in the pieces and placed in the flask with water for 5 minutes and then titrated. The student reported the volume of titrant used per trial for samples collected each day in the following table. 1. Complete the ionic equation for the reaction. So let's go back. Incomplete ionic equation is given and asked to complete it. So we have 5 iron 2 plus, we have 5 iron on the product side, we have MnO4, so we have 4 oxygen on the reactant side, but we have only 1 oxygen on the product side. So we can balance that by adding 4 water molecules. Next we need to balance the protons, so we have 8 hydrogens on the product side, so we can write down 8H plus here. So we can write down here 5 Fe2 plus we have MnO4 minus, plus we will have 8H plus, we will have 5 Fe3 plus we will have Mn2 plus we will have 4H2. The candidate used 25 centimeter cube burette with an uncertainty of 0.05 centimeter cube. Comment on the uncertainty recorded for the titrant volume. So in this table we have been given the titrant, which is obtained from the burette, reading the initial volume of the burette. So let's have a look at day 1. So the titrant given is 3.40 for first titration. So how student obtain this? So student read the burette with initial volume. For example, initial volume is 0.00 plus minus 0.05, and the final volume in this case for the first titration will be 3.40 plus minus 0.05. So change in volume, which is titrant, change in volume will be equal to 3.40, and the uncertainty will be plus minus 0.1 centimeter cube. So we can say is incorrect, and two readings, hence uncertainty should be plus minus 0.1 centimeter cube. 3. Calculate the initial percentage content of iron 2 plus in the raspinner showing your working. So if we go back and look in the questions, we have been given the concentration of KMnO4, which is 0.01 molar, and the day 1 we have average volume 3.38, and we can find out the moles of MnO4 minus. So N of MnO4 minus will be equal to 0.01 times by 3.38 divided by 1000. If I solve this, that will give me 3.38 times 10 to the power minus 5 moles of MnO4 minus. So the ratio. So ratio between MnO4 minus to Fe2 plus is 1 into 5. So the moles of N of Fe2 plus will be equal to 3.38 times 10 to the power minus 5 times by 5. If I solve this, that will give me 1.69 times by 10 to the power minus 4 moles. So the mass of iron will be equal to moles times by molar mass. So the mole is 1.69 times 10 to the power minus 4 times by the molar mass of iron is 55.8. If I solve this, that will give me 9.43 times by 10 to the power minus 3 gram. Next, we need to find out the percentage mass, percentage by mass. So the mass we find out is 9.43 times 10 to the power minus 3, and let's see what mass we started with. So we started with 2.0 gram divided by 2.0 times by 100. If I solve this, that will give me 0.47%. For the results calculated for subsequent days are shown. Comment on the significance of the difference in iron 2 plus content measured for day 4 and 5. So day 4 we have 0.11 plus minus 14.5%, and day 5 we have 0.09 plus minus 18.7%. So let's do some calculations. So 14.5% of 0.11 is equal to, solve this, so that will come as a 0.11 plus minus 0.0159, And for day 5, so 18.7% of 0.09 will be equal to 0.09 plus minus 0.0168. Okay, so almost, this is 0.016 and this is almost 0.017. Comment on the significance of the difference. There's no really any difference in terms of iron contents in day 4 and 5, and the reason why, the uncertainty ranges overlap. So the uncertainty ranges, they are overlap. So the difference between two values is not significant due to larger absolute uncertainties. Or we can say no difference and uncertainties larger than the difference. Suggest 2 flaws in the design that could have contributed to the random error in the investigation. So the one I have already highlighted when I was reading the question, so that is, so the spinach leaves were roughly torn in pieces. So spinach leaves, they were roughly torn. So how can we remove it? So making sure they are of same size. And the second one we can say, so we can dilute the titrant, so we can use a larger volume because the volume of titrant is small. So dilute the titrant, so use larger volume. 2. The student didn't standardize the KMnO4 solution used for the titration. Suggest what type of error this may cause, giving your reasons. So straight away will be systematic error. Will be systematic error. All values will be inaccurate. The titration of iron 2 with MnO4 minus in acetic medium is a redox reaction. State the oxidized and reduced species, including the change in oxidation state. So species oxidized is iron 2 plus to iron 3 plus, and the change in oxidation state is +2 to +3 for iron. Species reduced is MnO4 minus to Mn2 plus, and oxidation state change from +7 to +2. Oxidation is increase in oxidation number, so for iron +2 to +3, and reduction is decrease in oxidation number +7 to +2. 4. Spinach contains a large amount of antioxidant compounds, including ascorbic acid and oxalic acid. Predict how this will affect the accuracy of the result, mentioning the type of and the direction of the arrow. So 3 things. Oxalic acid, which is H2C2O4, do react with MnO4-, and there will be another redox titration happening at the same time. So the volume of MnO4 used will not be accurate. So we can say this is an example of systematic error. Systematic error, and accuracy will be low, so low accuracy. And because we will not have the correct volume of MnO4- used, so the estimation of ion will not be right, and it will be in a higher end. So we'll do the over estimation of ion 2, overestimation of ion 3. Physical properties of elements vary according to the atomic number. Section 6 to 9 of the data booklet lists some of the properties. A. Deduce, giving a reason, the group of elements in the periodic table most likely to undergo sublimation. Sublimation is when a solid directly goes into gaseous state. So a solid directly changes into gas. That is called sublimation. We are looking for a low difference between melting and boiling points. So let's have a look. So on x-axis we have atomic number given, and we have 2A, which is helium, and then we have 10, which is neon, and then we have 18 somewhere, which is argon. So helium we have here, we have neon, we have argon, and then next we have krypton, which is 36, so which is here, krypton, and then we have 54, which is xenon. So we can say group 18. Group 18, or we can say noble gases. Reason. So the reason why there is small difference between melting and boiling points. We can also say in terms of intermolecular forces. So they have weakest intermolecular forces, London dispersion forces. Hence they have low melting and boiling points. B. Describe the density trend across period 4 and 5 of the periodic table. So if we look in the periodic table, period 4, it starts with potassium, and period 5 starts with rubidium. So potassium has atomic number of 19. So let's look where the 19 is. So 19, around here we have 19. And period 4 ends at krypton, which is 36, so 32, 34, 5 and 36 here. So you can see it goes up and then it decreases. And period 5 starts with rubidium, and rubidium has atomic number 37. So 37 we have here. We can see again it goes up, and period 5 ends at xenon, which is 54. So 52 and 54, so it goes down again. Right, so describe the density trend across period 4 and 5 of the periodic table. So we can write down density increases and then decreases. Just reading the graph, basically, using the periodic table. 2. Suggest with a reason whether the lanthanides or actinides of F block would have the higher density. So let's go back the graph one more time. So lanthanide start with lanthanum 57. So 57, so we have 4, 6 and 7, somewhere starting from here. And actinides start from actinum 89, so which is somewhere here. Right, so you can see actinides, they have higher density. So actinides, and the reason why density increases down all the groups. Due to larger increase in atomic mass. Or we can say actinides, because they have a greater atomic mass with a similar type of bonding. So both they have similar type of bondings, but their atomic mass is greater. 3. Compare the ease of oxidation of S block and D block metals to their melting points and densities. Use section 25 of the data booklet, which is not there anymore in new specification. It was reactivity series in old specifications. So we know S blocks, they are less denser than D blocks, and they are more reactive than D blocks as well. So if they're more reactive, that means they can oxidize easily. So their tendency to give electron is a lot higher because they have low ionization energy. So we can say low densities oxidize easier, and D block, they have higher melting point because they have strong metallic bond compared to S block. You can say low melting point, oxidizes, low melting point oxidize easier. B4. Sketch how the first ionization energies of elements vary with the atomic radius. Atomic radius increases going down the group and ionization energy decreases going down the group. So the graph should look like this. 4. Powder zinc was reacted with 25 centimeter cube of 1 mole per dm cube copper 2 sulfate solution in an insulated beaker. The temperature was plotted against time. Estimate the time at which the powder zinc was placed in the beaker. So let's have a look in the graphs. You can see this is the point where zinc powder was added to copper sulfate, because we can see after that temperature start increasing. So that is 100 second. Estimate the time, so we can write down 100 second. Number 2, state what point y on the graph represents. So let's go back and have a look what is y. So the y represents the highest temperature recorded. So the y highest recorded temperature. We can say maximum temperature, or we can say is where the reaction completed, but the best answer is highest recorded temperature. The maximum temperature used to calculate the enthalpy of reaction was chosen at a point on extrapolated dotted lines. State the maximum temperature which should be used and outline one assumption made in choosing this experiment on extrapolated line. Let's go back and have a look. So we mixed zinc when time was 100, so we need to read from somewhere here, and each line represent 2, so we have 70 here, we have 72 here, and looks like 73. So 73 is the maximum temperature from extrapolation. So 73 degrees Celsius, and assumption we make is no heat lost. So no heat loss. 2. To determine the enthalpy of reaction, the experiment was carried out 5 times. The same volume and concentration of copper sulfate was used, but the mass of zinc was different each time. Suggest with the reason if the zinc or copper 2 sulfate should be in excess for each trial. There can be range of answers. Copper sulfate can be in excess because zinc is independent variable, or zinc can be in excess to determine the effect of zinc on temperature. I will write zinc. Results can be used to see if amount of zinc affects temperature rise. 3. Q is equal to mc delta T was used to calculate the energy released. The values used in the calculation were mass 25 gram, specific heat capacity 4.184 joule per gram per Kelvin. State assumptions made when using these values for mass and specific heat capacity. So the mass 25, we assume the density of solution is same like the density of water. Density of solution is 1.00 gram per centimeter cube, same as water. Second assumption we made, C specific heat capacity 4.18 joule per gram per Kelvin is specific heat capacity of water. So specific heat capacity of solution same as water. Predict, giving a reason how the final enthalpy of reaction calculated from this experiment would compare with the theoretical value. So to work out the percentage error. So the experimentally determined value will be lower, or we can say it will be less negative because it's exothermic, or less exothermic as heat loss to surrounding. That's the biggest error in this experiment. So it is a systematic error. So heat loss to the surrounding.